Happy Wednesday morning. And this is a recording from our meeting on this week 6 live online session. And this week we'll be looking at the blood vessels. And what I'm gonna focus on this session today is that we're gonna really mainly just review the chapter content on the chapter of the blood vessels. And as you might remember, our class yesterday on Tuesday, unfortunately, I had to move that fully online. So instead of completing a traditional lab this week, you actually completed an online lab all about the pulse. And I prepared you a rather nice video to go with that. So if you follow step by step that video, you should be all set, and it shouldn't have been too much of a hassle to tackle that lab. Like I said, today we'll go through just some of the main points of the chapter material for this week's chapter. Of course, obviously, we won't be able to cover everything in a great detail. So I have, as always, provided you full lecture videos on the learning module for this week. Then on Thursday, we get to meet again face-to-face, something that I'm really excited for and really looking forward to. And we'll kind of wrap up if there's any empty parts or any loose ends to finish off regarding the chapter content or the Pulse Lab. I also have a rather fun project for us where you actually get to apply the anatomy of the major blood vessels by preparing a map of what really matters. So that's the plan for this week. Do remember that on these Wednesday sessions, we have one session in the morning and one session in the evening. So do not feel that you have to attend to both of those. It's the same material that we cover on both of those. So it's up to you to choose whichever works best for you. Both of these sessions are planned to take about an hour. So it's kind of a nice condensed review of everything that matters. Two things that I really wanted to do today. I just wanted to remind you that the exam and practical, both of those, the final grades have been available for you for a while now. If you haven't had a chance, make sure you review the feedback of those. I take quite a bit of time to write individual feedback for everyone. So I really encourage you to look through those. Also, if you are missing any assignments or wish to retake any assignments, that would be the time to contact me and we will tackle those. Most of our time today is dedicated on reviewing the chapter material. We will look through a general blood vessel structure. We will talk about blood flow, blood pressure, and pulse. Another thing that I do want to remind you at this point is that you do have excellent tutoring available here at the college, and I've shared more details about that on our earlier classes. Do also remember that if you do want, I'm more than happy to make myself available to facilitate any one-on-one or group meetings. All you have to do is drop me a message and I will make sure that we find a time that works for you. But having said all that, just quickly, I guess that the thing that students are most interested always is that what is going to affect their final grade. So the format of this week's assignments is not too different from what you've seen before. We have our traditional quiz about the chapter material, and you have your practice anatomy, which is basically preparing you for the practical. And you should have at this point already completed our lab. And this week, like I said, it's going to be all online. So you look at the pulse points, and effects of various things on the pulse. So rather than doing a face-to-face lab, it's all going to be online this week. And as we are getting started, I think this is a good time for us to remind ourselves that, okay, so far we have talked about the blood. We took some time talking about the what blood is made of, what elements, characteristics of the blood, importance of the blood as a transport media, and so on. We've also talked about the heart, which you remember was probably one of my favorite topics, since that's something that I've been working on quite a big chunk of my career. So now to complete this review of the cardiovascular system, I think it only makes sense that we shift our focus to the blood vessels. And if you wanted to simplify the relationship of these three elements of the cardiovascular system, blood was basically the transport media. Heart was the pump that drove that transport media around. And blood vessels would be now this tubing within which all of this blood travels through. And I've said to you before that human cardiovascular system is a closed loop and one directional loop. So the blood goes one way and one way only, and it doesn't really end up leaving the cardiovascular system. There's a little bit of a but to that statement. So we'll look at, when we focus on the lymphatic system, some of the inaccuracies with that statement. But at large, it is a closed loop system as well. What I wanted to do was also to consider many reasons why cardiovascular system, and especially when it comes to the blood vessels, why you might want to know that. How does it relate to clinical practice? Of course, we can have bleedings of many different kinds when the blood vessels are damaged. If bleeding occurs underneath the skin, within the tissues, we can see that as a bruising. We can have issues with high and low blood pressure. There can be many different kinds of blockages, either for the flow of the blood or some sort of a blockage that travels within the cardiovascular system. So there's many reasons why understanding the cardiovascular system and the blood vessels is going to be very, very important for you as you are working towards the career on clinical practice. Now, what I would typically ask my students would be to think of the blood vessels, the different types of blood vessels that you know. And my students are typically pretty good about listing those, either in the chat if we are still in this remote mode, or if we are in the class just shouting out the answers. So I challenge you, even if you're just watching this recording, to think of as many different types of blood vessels as you can think of. And typically what I get from my students for this question is arteries, capillaries, and veins. And if you got that far, you're doing really well. However, I think that we're going to be able to do even better. So in addition to those, we're going to add arterioles, which are basically smaller versions of the arteries, located somewhere between the arteries and capillaries. And same goes for the venules, which are smaller versions of the veins between the capillaries and veins. And of course, we remember that arteries were all about carrying the blood away from the heart, and this blood typically in systemic circulation is oxygen rich. And veins were all about carrying the blood towards the heart, and in systemic circulation, this blood is low in oxygen. Of course, this is flipped around when we talk about the oxygen content of the blood, when we talk about the pulmonary circulation. But we're focusing now on these examples of the systemic circulation. What's interesting to me is that when we are studying blood vessels, we end up finding that there are the same three layers in all of these different types of blood vessels that we just saw. So it really doesn't matter which one we're looking, the general structure is the same. The proportions of these layers might vary a little bit, but in general, there's the same 3 layers. So we're going to go through that next. And these layers of the generalized model of the blood vessels are referred as tunics. So tunica is, if you're interested in history or history of clothing or anything like that, it is this kind of a layer of clothing that you put on, especially in the Mediterranean and ancient Mediterranean cultures. So basically just a linen folded in half with a hole for the head. So it's a layer of some kind of a clothing. So just as that, we refer to these layers of the blood vessel as tunicas. And let's have a look at the 3 layers that I promised to talk with you about. So the first one, the one that's closest to the very center, so the lumen of the blood vessel, is going to be our tunica intima. After that, tunica media, and the most external layer of the blood vessel is going to be our tunica externa. In some of the other parts of the world, rather than calling it tunica externa, we also might call it tunica adventitia. I think that that's especially more common in British-speaking world, but you might see either one of these words, so I want you to be familiar that that can happen. So let's look through each of these layers and have a little bit of an understanding what's going on with each. So we're going to start with the tunica intima, and how I always think of it is that, remember, the tunica intima is in intimate contact with the blood inside the blood vessel. So it is the innermost layer. Another thing that's worth noting is that tunica intima is made of simple squamous endothelial cells. So normally I would challenge my students to identify these cells here. And what they do end up picking pretty quick is that these are simple, so it's one layer, squamous, so these flattened disc-looking cells, and endothelial cells. And this really helps us to understand the role of the tunica intima when we look at the cells that this layer is made of. So what would this simple squamous endothelial cell layer be ideal? Well, let's think of that together a little bit. Well, first of all, it does provide protection. So when the blood flows within the blood vessel, it allows this easy, smooth flow of the blood within there. There's nothing that really interrupts the flow of blood, and it quite nicely just protects the layers that are more innermost of the general blood vessel structure, but it also facilitates smooth flow of the blood within these vessels. The other thing that we'll end up noticing is that this is a very thin and just a single layer of cells, so it's easy for materials to pass across this layer. So that's another thing that's noteworthy, that this structure facilitates easy passage of the materials. So that tells us about the characteristics of the tunica intima. And having said that, I think that we are in a good place to move on to have a look of the next layer. And next layer is going to be our tunica media. So this is the middle layer, if you wish. And this is typically the thickest layer of the all that we end up seeing of these 3. If we consider what this layer is made of, there's a great amount of smooth muscle and elastin present. And let's focus for a second of thinking of this smooth muscle, the amount of it and the importance of it. So you remember smooth muscle cells, they were able to adjust based on the need of contraction. And we found those very commonly in the intestinal tract and also around the blood vessels. These are not under conscious control, so they are involuntary. One of the important things that the smooth muscles would do for us when we think of the blood vessels, they facilitate two types of responses to the needs of the blood vessels. Well, when the blood vessel diameter needs to go down, so we shrink the diameter of the blood vessels, thanks to this smooth muscle layer, these blood vessels can now do vasoconstriction. So constriction referring to bringing the vessel diameter down. Vaso-dilation is just as well possible. And dilation, remember that word, referring to expanding the diameter of the blood vessel. So it's thanks to this smooth muscle layer in the tunica media that we're able to do these two types of responses when we are reacting to the needs of the body and needs of the circulatory system and how we divide blood and to what part. The final layer that I want to talk about is going to be Tunica Externa. And you might remember that I shared with you, this is sometimes also called Tunica adventitia. This is largely made of connective tissue. There's also nerves, lymphatic vessels, and so on present there. And the function of the Tunica Externa is really to reinforce the blood vessel structure, the walls of the blood vessel, and also anchor this blood vessel to its side. And now that we have talked about that, there's only one more, a little detail that I've included on this slide that I want to mention to you at this point. So, of course, we have different kinds of blood vessels, even though all of these blood vessels have these same three general layers. There's some amount of variety on blood vessels depending on where they are, what they are needed for, and so on. And some of the blood vessels end up being very thick and very big in size. And in response to that, we need to make sure that these thick, large blood vessels receive blood supply. Just as we saw with the coronary circulation of the heart needed a constant blood flow, so do the blood vessels. And this is where the structure known as vasa vasorum comes in important. These are basically the blood supply to the vessel wall of itself. So that's an adaptation to make sure that we get the blood supply to the vessel wall itself. And the reason why I'm bringing this up when we're talking about Tunica Externa is that, of course, Tunica Intima is in so direct contact with the blood that it really doesn't have a problem of not being supplied by blood, even if the vessel size would be large. Same goes for Tunica Media, the only small layer that separates it from the blood is the Tunica Intima, which of course wasn't super thick. So Tunica Media doesn't have this big problem either of having constant blood supply. It is within the Tunica Externa where the vasa vasorum becomes important that we ensure that this layer of the blood vessels receives the constant blood supply as well if we have a very thick blood vessel. Now that we've reviewed the general structure of these blood vessels, I think it's useful to look at this diagram where we have a general artery and a general vein, and we even have capillaries here. And when we really pay attention to the structure of these blood vessels. We see there's some similarities, some differences, but most importantly, what we end up seeing that each of these blood vessels contains these three layers: Tunica Media, Tunica Externa, and of course, innermost Tunica Intima. Capillaries are a little bit of a different story. There we only find one layer, and we'll talk about that in just a second. But what I want to shift our focus now on is that I want to spend a little bit of time for us to go through all of the different types of blood vessels. So this first part is going to be a little bit more anatomy oriented, and the second part of the session we're going to move on to pay a little bit more attention on the physiology aspects. So let's start by discussing about arteries. And like I mentioned, this is blood that's flowing away from the heart, and in systemic circulation, this blood would be typically rich in oxygen. So the blood has returned from the lungs, it's now rich in oxygen, and it's ready to flow to the other parts of the body carrying that oxygen with it. This is in systemic circulation. Of course, in pulmonary circulation, this blood now would be low in oxygen and it'd be going to the lungs to get reoxygenated. So what I want to spend time on a little bit is for us to have a look of the differences on a microscopic level between arteries and veins. So here I have a microscopic image where we have just conveniently two blood vessels right next to each other. One of these is an artery and one of these is a vein. And again, I would typically ask my students to identify which one would be which one. And usually students are pretty good at spotting that the arteries have much thicker wall that's much more rigid. So even when the blood has been drained out of the arteries, their blood vessel wall still maintains its shape. If we compare it to the vein next to it, you'll see that veins tend to collapse, kind of just lose their structure when they're emptied from the blood inside them. So we can really see the difference between arteries and veins even on this level. And I've shared with you that I've spent much of my professional career working with catheters. And one way to tell apart the arteries and veins that I find much more useful than just looking at things is to really feel it. So sometimes in anatomy and physiology, especially if you're working with catheters, you just need to feel the difference between an artery and vein. And arteries really do feel much more firmer. So it's all about being able to compare structures. So something to keep on mind. So I guess that since we have made a note now that we are comfortable with knowing that our arteries were much more thicker, it would be a good idea to pay a little bit of attention on figuring out why this might be the case. So first of all, they're thick and they're also elastic. This all goes back to where arteries are located. They're located just after the heart. So this is the area of the cardiovascular system that receives the blood at the highest pressure, shooting out from the heart in a pulsatile manner. So these vessels really are under quite a lot of pressure. So responding and handling this, and also to a certain extent smoothing this pulsatile flow of blood out from the heart. There are different subgroups of arteries, and I think it would be good for us to go through those just quickly. The full story you will be able to see in the full lecture videos. But let's start with elastic arteries and have a look of those a little bit. When we talk about elastic arteries, these are the blood vessels such as aorta and its branches that are located right after the heart. So the very first ones there, they are characterized by this very thick wall of this blood vessel. So they're very, very thick. Also, their lumen facilitates the flow of blood with a very low resistance to it. And one other term that we sometimes see being used when we discuss about elastic arteries is that they are described as conducting arteries. This really explains what they are there for. So they're there for carrying the blood from one part to another. They don't really do much in terms of playing role in choosing where the blood goes or anything like that. They simply conduct the blood onwards. What else could I say about them? Well, there's a lot of elastin on the elastic arteries, so that's probably not a huge surprise when you think of the composition of these arteries. One thing that's interesting, there is no vasoconstriction available at all on these elastic arteries. So they're not able to really systematically change their diameter in response to body needs. So they always just facilitate the flow of the blood. So they conduct the blood. They don't do much of a choosing or controlling where that blood goes and in how great amounts. They do tend to have a good amount of expanding and recoiling. And this relates to the fact that these elastic arteries, well, they receive this high blood pressure pulsatile flow of blood, and they kind of tend to control the blood and the blood that's coming out in terms of evening out some of that variation in the pulsatile flow, smoothing out some of that variation of high-low, high-low, high-low blood pressure. So one way that we describe them sometimes is that they function as pressure reservoirs. And by that, I really mean that they're able to, when there's a high pressure, adjust to that. When there's low pressure, they're able to kind of then recoil in response to that. So overall, we try to keep the blood pressure more consistent and more consistent than what it would be when it would be shooting out of the heart. Well, the next types of arteries that I wanted to discuss about is going to be our muscular arteries. So these are located, if we follow the path of blood vessels starting from the heart, a little further than the elastic arteries. And in fact, most of the arteries are classified as muscular arteries. So these arteries that we study and we name, most of those are going to be muscular arteries. These are the thickest of all of the arteries that we end up seeing, and they do have a very thick Tunica Media layer. So that's something to bear in mind. Well, if we know that Tunica Media is thick, that gives us a clue about what these muscular arteries would do. Well, of course, we remember that Tunica Media contained the smooth muscle layer. So if there's a lot of smooth muscle, that will have an effect on how these arteries will behave. There is a little elastic tissue as well, and this, of course, allows us to do vasoconstriction. So we're now able to expand and shrink in response to where we want the blood to go. So we're able to choose where the blood travels. And this is where the name distributing arteries comes from, that we typically associate with these muscular arteries. So we're able to choose where do we distribute the blood to. by controlling the flow of the blood on these muscular arteries. So either sending it to certain areas in greater quantities or lesser quantities. So that's why they're distributing arteries. And the last type that I wanted to discuss is going to be our arterioles. And you remember that earlier on I had arterioles as a separate structure there. You can definitely consider it as such. So eventually what we end up seeing when we keep following the path of arteries away from the heart is just a single layer of cells on these arterioles. And this single layer of cells that we see on the arterioles is of course going to be our Tunica Intima layer. And there's another important structure that I want to discuss when it comes to the arterioles before the capillaries. And this is our pre-capillary sphincters. So what pre-capillary sphincters are? These are these bands of muscle tissue before we get to the capillaries. And these bands of muscle tissue work so that they can choose to keep the blood vessel open, or they can squeeze and close off that blood vessel. So they essentially are gatekeepers that choose whether the blood flows into the capillary network or not. So they open and close capillary networks as needed. On this diagram that I have here on the screen, all of these pre-capillary sphincters are open, so they're allowing the blood to flow to all parts of this capillary network. And if you think of the arterioles, if you think of the capillaries, the main function here is the exchange of materials from the inside of the blood vessel to the outside of the blood vessel. So if we want a lot of this exchange to happen, we want to get as much blood going into the capillary network as possible. And this is possible because of these pre-capillary sphincters being open. We recruit as much of this capillary network as possible. This is not always the case. Sometimes we close these pre-capillary sphincters, so we block the blood from going into these capillaries. So we do not want blood spending time going to these capillary networks. We simply want the blood to travel through that area to somewhere else where we think that is more needed. So pre-capillary sphincters can be also closed. What's important to notice here is that we actually have more capillaries in our body than we have blood. So if all of the capillary beds were open at the same time, we would run out of the blood. So for that reason, we need to do some choosing of where the blood is going to go to. So we choose to a certain amount to always open only some of the capillary networks. So pre-capillary sphincters, an important structure for that for you to know. And that brings us nicely to talk about the capillaries. And you remember that capillaries were these smallest of blood vessels that we saw when we compared these. So these are these microscopic small vessels. The diameter of a capillary can be as small as only about one red blood cell. So only one red blood cell might be squeezing through a single capillary at the time. What we end up finding with the capillaries is that the wall of capillaries is made of only Tunica Intima. So you remember the innermost general layer of a blood vessel. The capillaries are the main site of exchange of materials. So these supply the cells and interstitial fluid that are outside the cardiovascular system. So we do end up finding capillaries everywhere in the body. And what sort of things could we have exchanging from the capillaries to the other places? We could have gases, nutrients, waste products, hormones, and so on. So it is really the passage of small solid and fluid particles that becomes important. And I want to go through 3 different types of capillaries with you. And we're going to start with what we know as continuous capillaries. Continuous capillaries can be understood really well based on the name that we've given to these. These capillaries are found typically, for example, in skin, muscles, lungs, central nervous system, and so on. Also including the blood-brain barrier. This was the special type of barrier that separated the cardiovascular system from the circulatory system of the brain, so there was no direct passage for the materials. But if we look at the continuous capillaries, the capillary wall is continuous, there's no gaps, cells are tightly attached next to each other, so they form a continuous wall. So that's where the name comes. And if the wall is continuous, it's easy for the material just to flow through. There's a good flow through these continuous capillaries. The next one differs a little bit from that. We call this next example fenestrated capillary. As you'll see, these fenestrated capillaries have holes on their wall. You can describe them looking a little bit like Swiss cheese if you wish. And interestingly, again, you know already, since you've spent some time on this semester with me in a class, I love languages and I love trying to understand where the names come from. And I believe, and this I have to say that I haven't checked, so I might be a little wrong. The term fenestration refers to windows, and I think to a French word of window. So you can think of these fenestrated capillaries as having little windows on their vessel wall. So that's where the term fenestrated comes from. Well, why does this matter? Why is this important? These types of capillaries are especially ideally adapted to things such as filtration, absorption, and secretion. This is because these little fenestrations allow materials to cross in and out much more easily than what we saw on the continuous capillaries. So little windows to facilitate this movement. So that's our fenestrated capillaries. It's not going to be a surprise to you that then when we get to the sinusoidal capillaries, these have something way bigger than just these fenestrations. There we have actually significant portions of the capillary wall missing. So it's no longer just small holes, but it's chunks that are missing. So you remember the term sinus? We've discussed that in a class. It was some sort of an empty space in an anatomical medical language. Well, sinusoidal capillaries have now a lot of these empty spaces. We typically find sinusoidal capillaries in liver, bone marrow, spleen. Another example that I can think of is adrenal medulla. These are especially good for clearing the blood. So again, these big chunks of wall missing, allowing a lot of material to cross in and out. The other thing that we notice is that since the wall of these sinusoidal capillaries is not completely smooth, the flow of blood within these capillaries, it goes down. We have slower flow of blood in this capillary type. And why this is important is that by having a slower flow of blood, now we have more time to actually process the blood that flows through this capillary type. So there's a lot of exchange going on here. So that's our capillaries. And I think we're good to move on and look at venules and veins as the next. So remember, veins were typically the blood that's heading towards the heart, typically low in oxygen concentration in the systemic circulation. And interestingly, what we end up finding is that we have a low blood pressure in veins as well. And we'll discuss that in just a second. Another thing that I want to discuss is that the wall of the veins is much thinner. We saw that when we looked at that microscopic image. So this explains why the blood pressure within veins has to be smaller. If the blood pressure was very high, it would be easy for us by accident to break these walls of the veins. Most of the blood vessels are actually veins in the body. So now the question that I ask from my students in a class that I think is a very good question is that, okay, we have blood that circulates in the body, circulates to all parts of the body. Now the blood has reached, let's say, for example, our toes, big toes at the end of the lower limbs. How does the blood get back from there to the heart? And students are very good at coming up with all sorts of explanations. Sometimes I hear it's that the new blood is pushing the old blood away towards the heart. Or the other thing that I hear is that the heart is sucking the blood back to it. Both of those play a small role, but really not the big role. The biggest reason why we get blood returning back to the heart is thanks to this special adaptation known as venous return. So you remember that I shared just a moment ago that veins had a thin wall. Well, what we end up finding is that a lot of the time veins get squashed by skeletal muscles around them. And as the vein gets squashed, these skeletal muscles help to push blood back towards the heart. Well, all this makes sense so far, but I guess you would ask me what happens when you stop squeezing that blood vessel. Doesn't the blood just flow backwards, downwards then? Well, this does not happen because we have this adaptation on the veins that we've already seen before with the hearts. We have valves present in veins. So rather than letting blood head backwards from where it came, we stop this from happening and facilitate unidirectional flow of blood only back towards the heart. So this is how this combination of having thin blood vessel walls at the veins, how them being squashed by skeletal muscles, which then push the blood towards the heart, right? And also having these valves that facilitated only unidirectional flow of blood. All of these factors acting together help with returning the blood back to the heart. So the process of venous return. Okay, this has a clinical importance that's very important. Have you ever watched a military march or a parade or anything like that? Well, often these soldiers or members of the armed forces are wearing their full uniform or at least their celebratory uniform. And every now and then you see one of them passing out. I spent a lot of time in the UK, so that's why I've picked this example. Why does this happen? This is because the venous return, the return of blood back to the heart, has now been compromised. When you stand with your knees locked, you're no longer doing that a little constant moving that we would normally be moving that would be helping us to push the blood back to the heart. Now, all of a sudden, the blood is not moving to the heart. We're consciously eliminating what not naturally happens. We just naturally constantly move a little bit. Even when you're sleeping, you're turning around a little bit, even if you think that you're not. Well, if we stop all that from happening, we're not getting blood back to the heart. And if we're not getting blood back to the heart, we don't have anything to pump out of there. And the first part that's going to be super sensitive if you're not getting blood back is the brain. So if blood supply to the brain is compromised, what happens? We need to somehow stop that situation from happening because brain will get damaged really easily. The easiest way to fix that is that let's have the individual collapse and lay flat, because now blood can easily flow back to the heart. So let's eliminate the effect of gravity. So that's why we do pass out if we're not getting the venous return working. Another clinical relevance is, of course, our varicose veins. This is what happens when some of these valves that we saw earlier on fail and blood ends up flowing back downwards following the gravity and now pooling up where the next valve is that's actually functional. So we get this big blood pooling on a blood vessel on top of a valve because of the valves higher up having failed. So this can be sometimes an issue. This can not be an issue. There's many different factors that play a role, even to the point that some have speculated is the job playing a role, for example, in aviation industry and so on. So that's all the kind of basic stuff that we need to know. And at this point, it's a good time for us to check if you have any questions. You remember you can always ask them during the class, in a chat, unmute yourself, or you can send me questions as messages on your learning management system, Canvas as well. What I do want to spend a little bit of a time, and we're not going to do the icebreaker, we're just going to jump right to the measurements and measures of the vascular system. So the first thing that I want us to look at is the blood flow. So the measure of blood flow tells us the volume of the blood that flows through in a given amount of time. And typically this is measured in milliliters per minute. Another measure that's going to be important is going to be our blood pressure, often abbreviated as BP in our medical notes. So this is really the force that's pushed by the blood against the blood vessel walls. So there's a certain amount of the force that blood pushes against the vessel walls. And this force is what we know as blood pressure. And this is measured as millimeters of mercury. So that's where the mmHg comes from. Well, what you'll see is that we have two values for the blood pressure that we typically record. We have a higher and then we have a lower value. Now, I would reach out to you and ask, why? Why do we measure two values for blood pressure? Well, if you completed the Pulse Lab this Tuesday, you remember that we saw a slide like this on the lecture videos that I provided for that. Blood flow in the body is pulsatile, especially at the arteries and closer to the heart. So you remember that during the diastole of the ventricles, blood just flowed nicely through the vessels. The vessels were they're a normal diameter. But when the ventricles contract, they're really pushing that blood out. Well, vessels, and especially our arteries, get all of a sudden a surge of a high amount of blood going through them. So they might need to have some amount of expansion on their vessel diameter. So they expand, they grow bigger in their diameter. So that's this varying pulse that we end up seeing, that blood doesn't get pumped out of the heart at a constant rate. It comes kind of in surges. And this explains why we actually get two measures for the blood pressure as well. So the higher value is known as our systolic value, and this is what gets measured when the ventricles squeeze, and the lower value, our diastolic value, is when the ventricles relax. There's many different factors that affect our blood pressure, anything from the volume of blood, the cardiac output, resistance to the flow, and so on. Well, now another question that I would ask from you is that has any one of you ever gone to a doctor and they've taken your blood pressure and you're like, oh, that's higher than it normally would be, especially if you have a blood pressure cuff at home, and then you go to a doctor and all of a sudden it's higher than it normally. Well, this is known as a white coat syndrome, and that happens to the best of us. So it is really when you have a higher blood pressure due to a stress of seeing a doctor or a nurse or something like that. And that's not totally uncommon. Anyone who has had their reflexes known, you're sitting there wondering that, oh, they're going to hit my knee. Is it going to jerk the right way or not wrong way? You're kind of starting to stress about things, and that's the same. Next thing that I would normally talk in a class with you guys is about pulse. But since we completed the lab on pulse on Tuesday, I'm not going to spend more time on that. I'm simply going to add a video about a pulse to the end of the video of this video, and you can click on there if you missed that part or if you're still confused what the pulse is all about. So we can talk through all that there. I do want to talk a little bit about the regulation of the blood pressure. And this is where, if you remember, I told you early on this course that it is a word of learning the homeostatic regulation loop, how homeostasis is regulated in your body. And I said that rather than learning all these complex diagrams, for my class, you only need to learn 4 spots, 5 elements of it. So first, something happened. This is usually a change. We detect that with a sensor. This information gets passed to the control center, which is typically the brain, and within there we have a set point for normal values of what the stimulus should be. If the stimulus is something else than within the set point, we are going to act on it. And usually what happened, we try to stop the stimulus from happening. There were only 3 examples that I could think of to share with you about when we actually promote the stimulus to happen. So most of the time it's going to be negative feedback. Positive feedback, childbirth, lactation, and blood clotting. Those were the only 3 times that I could think of when we saw positive feedback. Okay, now that we've reviewed the homeostatic regulation loop, so the goal of that was to maintain consistent internal environment. We can use that same graph, that same mechanism of analyzing things, and we can use that to go through 4 different ways how blood pressure can be regulated in short term. So let's start with a stimulus. That stimulus is going to be a change in the blood pressure. Blood pressure is off. And what is it off? It's off from our set point. This could be 120 over 80 or 120 over 90, depending on what years numbers you're looking. They keep changing a little bit, the recommended values. I think 120 over 80 would be probably more accurate. Well, we're noticing that the stimulus, the blood pressure, is not what it should be in the set point. We have to sometimes notice it. And how we notice it is through these sensors. So we have some types of receptors that help us to notice that. So let's go through that. What sort of receptors could we have for that? We have receptors that are located at the carotid sinus. So you remember common carotid artery at your neck, divided pretty soon into 2 branches, external carotid artery and internal carotid artery. And right there, we end up seeing an expansion on the carotid artery, and this is known as a carotid sinus. So we have receptors there. Another place where we end up seeing receptors for blood pressure is within our aortic arch. So you remember blood coming from the heart, and then we had the 3 major vessels that aroused or came out from the aortic arch. So we have receptors there as well for the blood pressure. We're detecting, is the blood pressure what it should be? And of course, all over in our large vessels. So all of these are receptors that help us to detect, is the blood pressure where we're expecting it to be, and we're comparing it to the set point. And of course, the control center, like I said, it is within the brain, and in particular for the blood pressure within the medulla oblongata, often just called medulla. Remember, this is one of the more early developed parts of your body, both in your individual development, but also in evolution, very well protected, very important structure. Well, what do we do if we see that we have our blood pressure that didn't match the set point? We're detecting that with receptors. We're going to act on that. And there's a few different ways how we can act on that. We can use medications to deal with the blood pressure issues. We can, of course, simply try to treat the cause, or we can use, as a shorter term response, vasodilation or vasoconstriction, so controlling the blood vessel diameter. So these are the short-term regulation approaches. Long-term regulation of blood pressure gets a little bit more complex, and this all is through the kidneys. Changing the blood volume changes then the blood pressure. And I provided an explanation of this in your lecture videos, so I won't go into them into that on this time and this review that we're having now. I just want to highlight that we have a direct mechanism, which is all to do with eliminating the volume by urinating some out, or preserving the volume by conserving water. We also have something that's known as an indirect mechanism, which is much more complex, and that's sometimes referred as a renin-angiotensin-aldosterone mechanism. So if you're interested on that, you can definitely study that on our full lecture videos. A couple of things that I want to just highlight to summarize really about the blood is that we want to have high enough blood pressure so that we are getting enough blood to all of the tissues, but we don't want it to be too high so that we would damage the blood vessels. So finding this golden spot where the blood pressure is just right is gonna be the challenge. And again, any questions, I'm always so happy to entertain those. I want to quickly finish off this review session by discussing about a couple of things that affect blood pressure. So there's many factors that play a role, and we're going to focus on talking of two situations. What happens when you have too high blood pressure, and what happens when you have too low blood pressure? So let's talk about hypertension first. That is when we have high blood pressure, typically 140/90 or higher, and that's a consistently elevated blood pressure. It's not just peaking in response to something. Why this could be dangerous is that you end up with a higher risk of heart failure, vascular disease, renal failure. You remember the kidneys filter the blood, or stroke. As a result, the heart needs to work harder. And what we actually end up noticing is that the myocardium ends up getting a lot of thicker in these patients with elevated blood pressure. So we end up with this thickening of the ventricles especially. Of course, there's also a buildup of plaque. So this results, even though the heart is thicker, the heart muscle wall, it is weaker and it is this flabby, so it's not functioning that well. Some of the risk factors that are associated with the hypertension, high blood pressure, include your hereditary factors, so you inherit a risk for that. Your diet, high in fat or in cholesterol, could be an issue. Obesity, age, diabetes has been associated with higher blood pressure. Stress, smoking, but often there is no one clear cause why one would end up with hypertension, high blood pressure. And what can you do? You can change your diet to low salt, fat, cholesterol, do exercising, lose some weight, stop smoking, and do medications. So all those healthy lifestyle choices. Now, I want to move on and look at an opposite situation where we have hypotension. In hypotension, we have low blood pressure. So the numbers that I picked here is 90/60 or less. Usually this is not as much of an issue as we had with hypertension, as long as the adequate blood supply to the tissues is still maintained. This might not be as concerned. Some research, and this is just early research, we don't have definite facts. Some research has indicated that it might even be beneficial. This is associated sometimes with a little bit longer life expectancy and less of cardiac illnesses. There's subtypes for hypotension, so let's have a look of those. So this can be just due to a temporary low blood pressure, for example, getting dizzy when you stand up. You can have a chronic hypotension. So this is often associated with poor nutrition, and you end up with a risk of developing many other conditions. And acute low blood pressure is usually indicative of a shock. And I know that our textbook really doesn't go into too much of a shock, but I do want to talk about shock with you because it is so important. And I love our mnemonics, and we're going to use a mnemonic we call in UK cops as police constables, and we love to use them in our mnemonics. So signs and symptoms of a shock would make a really good exam question. So let's go through those. First of all, when you're about to go into a shock, you end up being kind of a pale. Your skin is kind of pale, whitish color. And the skin also feels cold and clammy, so there's not as much blood going to the skin. So it doesn't have that red color that we would normally get when blood is present in the skin. The blood usually brings also some warmth to the skin, so there's not that. It feels cold. It can feel clammy as well, kind of a little sweaty. The other thing, the breathing of an individual who's going into the shock tends to be very fast, but very shallow. So they're not taking deep breaths. They're just going. Also, same goes for the pulse. It is fast and weak pulse. So you might have hard time finding the pulse on this individual going to a shock. It is rapid, but it's not strong. These individuals tend to be agitated. They are really not feeling well. Often they end up saying that they're very thirsty. They want to drink something. And if you get all of these, you are likely to find that the individual is going to be going into the shock. So PC FATS is a good mnemonic for remembering signs and symptoms of the shock. And if we were in a classroom, this would be the time when I would now teach you how to treat shock. But we're not going to do that since we are not in a classroom. Hopefully we'll get to do that on a Thursday. So let's have a look of a little bit of a few other important things to notice. We're going to talk about the control of the blood flow. So this is enabled to be constantly controlled by sympathetic nervous system and hormones. These are the extrinsic control of the blood flow, and intrinsic control is by adjusting this then to meet the local needs by the capillary control. And we would look at typically the special circulations at different parts of the body, but I'm going to save this for our class activity on this coming Thursday. So we'll notice, for example, that skeletal muscles can go from receiving about 20% of the blood supply to as high as 70%. So there's really a high amount of growth that we can direct the blood to the skeletal muscles based on their needs. A brain needed a constant blood flow that's steady, so it cannot be too high, it cannot be too low. Neurons die easily, so there's a special circulation adaptations there. Skin is excellent for thermoregulation and acts as a blood reservoir. Lungs needed low blood pressure. And heart, well, we talked about the coronary circulation already earlier on in this course. So the speed of flow of the blood is highest at the aorta and then drops when we get to the capillaries. And the slow speed of blood at the capillaries is explained when we think of what happens at the capillaries. This is the site where we exchange the materials. So we don't want the blood to flow through too fast. We want to give the time that materials can be exchanged at this site. And again, the flow then increases a little bit again once we get to the veins. Why would this be the case though? We know why it makes sense to have a slow flow in the capillaries, but what causes the flow to be so slow in capillaries? Well, this is all dependent on the cross-sectional surface area of the vessels when added together. So something to keep on mind. That would make a really good question, having those graphs and having you to interpret a little bit. What do they tell us? What would it be useful? Why do we want to really understand these graphs? Why are they important? Let's have a look of the, so again, just this diagram is here to remind the exchange of materials at the capillaries. That's why we had a slow flow there, but actually the total volume of the capillaries, the total cross-sectional area is very large here. The bulk movement of the fluids, we're going to be talking about osmotic pressure and hydrostatic pressure. So osmotic pressure is really this pressure of being pushed into the blood vessel, and hydrostatic being pushed out from the vessel. And we'll talk about the balance of those, why it's important when we move on to talk about the lymphatic system. If this is not in balance, the hydrostatic and osmotic pressures, we can end up with an edema. So the amount of interstitial fluid, so the fluid that leaks out of the blood vessel, because the same amount is not being put back in as escapes, there's more now fluid outside the vessels, and we end up with this increased amount of interstitial fluid. How you can tell that it is an edema? No, it's not just someone being chubby. It's when you push that area, it does leave an indentation there. That will eventually disappear, but you will initially see it there. Final couple of points that I want to make and remind us that arteries typically run deeper than the veins. And that makes sense. We want to protect them. You don't want to cut your arteries. That's why arteries are deeper in the body, because if you cut an artery, you can lose blood a high amount in a very short amount of time. Veins are typically a little bit more superficial. We do have some deep veins as well, but they are typically a little bit more superficial. There's low blood pressure in these, remember, so we do not want to squeeze them too much. We do squeeze them somewhat though for the venous return. Another thing, veins are much more interconnected, so there's many alternative routes for the veins to find their path, and for the blood to find their path. So that's why studying veins is a little bit harder than studying arteries. Arteries are usually much more regular from one individual to another. Veins, there's a lot more variation. And of course, brain needs a unique drainage of the blood from there. And intestines, we remember that all the blood goes initially to the liver to store energy within the intestines. So otherwise your body would just end up burning off that energy like crazy. So those are the important things that I wanted to highlight from this chapter. It has been a lot of material, but it is a condensed version from all of the lecture material that you can find on this week's module. We will get to apply this information a lot more on our class tomorrow. In the class on Thursday, I have some rather exciting activities lined up for us. And of course, you got to learn a lot more about the pulse on our virtual lab, which you completed yesterday. If you didn't get around to it, this is a good time. Remember, it's going to be due at the end of this week, so make sure you get that done. We don't have traditional face-to-face lab to complete for this week. It is going to be this virtual lab. And on that note, that really completes everything I was planning to share with you today. I appreciate you joining me. I am going to have this session repeated again on in the evening at 8 o'clock. So you're more than welcome to join me there as well. It is going to be the same material, so if you can't make it, you might want to consider watching a recording either from this session or that session, and that will get you up to speed with everything that you should know at this point about the blood vessels. Again, as always, I so appreciate you being part of this class. It is definitely one of my favorite things to do, to work with you guys. That's what I love about my job, and I think we have a really, really good team on this class this semester, so we're gonna be able to accomplish great stuff, and I look forward to seeing you all in person on tomorrow's face-to-face class. Until then, have a very good rest of the day. Bye.